talk of the season. We will be resuming mid-September. So sorry to break your hearts. Today we have Drew joining us from JOA Surveys, and he's going to talk a little bit about creating a tide book.
All right, I didn't realize I was the closer. Thanks all for showing up. Lots of familiar faces out there. Always good to see my Cordova family. For those that don't know me, real quickly, I grew up in Cordova, class of '09.
Speak up a little more.
Yeah, sorry. So for those that don't know me, I grew up in Cordova, graduated from CHS in '09. My dad's a fisherman, so I kind of grew up fishing. Did all the fun science center education things like Discovery Room and these Tuesday night talks and Ocean Science Bowl and all that stuff. Just wanted to plug them a little bit because I thought that was a really great part of growing up in Cordova. I also was a fisherman for a while, so I grew up fishing with my dad, and then did a couple of tours over in Bristol Bay, served my time there. Came back, did some seining for a couple of years in the Sound, and then bought my own gill netter at one point and fished that for a little while, and then kind of realized I wanted to get back into science a little bit more and turn that page over. Might be back though at some point, we'll see. I went to Western Washington University, got my bachelor's of science in environmental science there. And then I kind of stumbled into this job with JOA Surveys. Kind of found out about them, went on their website and read cool things about what they did and just called them and gave them my resume and ended up getting a job. I also have kind of a side hustle of making the Avenza maps of the flats that a lot of fishermen here use. Just came out this morning.
Already downloaded.
Okay, good. So a little bit about JOA Surveys. We're based in Anchorage. It's a pretty small company. When I joined about 6 years ago now, it was the 3 owners and I was the only employee. So we've been growing a little bit recently. We're maybe up to actually a dozen full-time employees now. They've been installing tide gauges and all this stuff since 2003. Map over there shows all those dots. We've either put a tide gauge there or maintained a tide gauge there. So we really get around. It's a pretty niche thing that we do. There's maybe 1 or 2 other private companies out there that kind of do this tide gauge work in the country. And so we get calls from all over the place. Of course, we specialize in Alaska, but we'll go wherever we need to.
What's the map above Hawaii?
This one right here.
Yeah.
This is Wake Island.
Oh, yes.
And this is American Samoa.
Okay.
We had a project out there.
Last year.
We have also been to Hawaii, though, actually. Actually, we were just there a couple of months ago, and I don't think this map has been updated since then. So, our main clients are NOAA, and so NOAA operates a whole network of permanent tide stations all over the country, and then they also contract out temporary tide station installs all over the place. So I'm not exactly sure what the percentage is, but probably like at least 80% of our work comes from NOAA. And then smaller pieces of the pie, USGS, Park Service, Army Corps of Engineers, State of Alaska, and then a little bit private private work. It's like sometimes in like related to like telecom stuff or pipelines and that sort of thing. Private coastal infrastructure projects. So a little bit more about what sets our company apart from like what you typically think of as a surveying company. We don't do like property surveying or construction surveying really. We're more in this area of like geodetic surveying, which is kind of like this more of a sciencey type of surveying. Geodesy is the science of measuring the earth. And so it's kind of like surveying with a sciencey flavor to it, which is pretty fun. It's cool. We're really kind of at the interface between science and like practical application of that science. And it's a really cool space to work in. It's really rewarding because you're, you know, as a research scientist, you're kind of sometimes at risk of getting a little bit isolated in your research, and you don't get to see like upfront the implications of your work. Even though you might know the implications of your work, you don't necessarily get to see it firsthand. And so in this job, we're really like out there getting our hands dirty, applying science. It's great.
What was that word, Drew? Geodesy?
Geodesy.
Geodesy?
Yeah.
Like Odyssey, but geodesy.
Geodesy, yeah. It's the science of measuring the earth. Yeah. It's a fun word to throw out there. Okay, so diving into a little bit of like just basic tide stuff. I'm sure you know this audience is pretty knowledgeable about this already, but so we've got sun orbiting, the moon orbiting the earth. They have gravitational pull, and that pull is creating a bulge of water on the earth. And as they orbit around, that bulge is moving, and they're moving in these patterns that are somewhat predictable. And that's what we call the tide. I wanted to point out two sort of configurations here that create some of the sort of monthly patterns that we see. So when the moon and the sun are aligned with each other, we get larger than typical tides, and we call them spring tides, not to be confused with the season spring. These actually happen twice a month, or twice a lunar cycle to be specific, but about twice a month. And then the other configuration is when the moon and the sun are not aligned or at right angles to each other. And that's when we get the smallest tides of the month. And those are called neap tides. Okay, diving into a little bit more science here. When we're trying to predict tides, we need some sort of mathematical model to sort of approximate what the tides are doing out there. And the way the scientists break it down is by these different tidal constituents. And each constituent is kind of the result of one specific celestial phenomenon that has sort of a fixed period. So like the orbit of the sun has a very fixed period of 24 hours. That's one of the tidal constituents. I'm not going to pretend to know what each of these actually mean, but the point is there's all these different celestial phenomenon happening, and each of them has a set of parameters that we have to figure out in order to predict the tides. And each constituent is modeled by a sine curve. And so the numbers for each constituent here get taken and put into a formula, and we get this nice curve out of it. And that's one constituent. And then we get the next one and the next one, and get a whole bunch of them. This is just a small selection of the constituents for Cordova. Once you get a bunch of them figured out, then you just add them all together, and you get this sort of composite compound curve, and that is your model for the tide. Usually we want at least 1 month, ideally 3 months of water level observations at the site that we're trying to predict in order to accurately calculate all these constituents so that the predictions are accurate. 1 month is really the minimum. 3 months, you get kind of a lot of bang for your buck in terms of increasing the accuracy of your predictions in those first couple of months. After that point, you start getting diminishing returns, collecting a year of data or 2 years of data. You're only improving your predictions by a little bit. So, of course, it's difficult and expensive to keep tide gauges alive in Alaska. So, a lot of times we're just kind of getting by with the minimum there as best we can. And then there's also this complication of atmospheric effects. So we talked about celestial phenomenon, the orbits and gravity and all that. But weather also has an impact. I'm sure you all know that. Air pressure and winds move water around. Let me see if I can get this video to play. This is a video I took, when was this? December 2022, just down the road here. If you remember when the white shed was kind of like starting to wash out there, there was a storm surge going on and also particularly large tides on that day. And this is the tide curve from the tide gauge that is here in Cordova by the ferry dock. And you can see we actually got about a meter and a half, or a foot to a foot and a half higher water than was predicted just because of the weather. And interesting note, the highest ever recorded in Cordova by the tide gauge was a 17.5-foot tide in 1981.
You know where Cordova Rose is? Bob Urbanson,
Yeah,
tide gauge there, and he moved his barge on shore, and according to him, it was an 18.2 foot storm tide.
Oh, wow. Huh.
I don't know when that was, it could have been 81.
Huh. Yeah. Well, in Cordova, we don't often notice these storm surges that much just because our tide range is so big, and so they kind of get diluted out, except in like situations like this where it's actually affecting our infrastructure. This is a chart of the tides over just this last month up in Prudhoe Bay. There's a NOAA tide station up there. And it's actually a really unique tide station. I don't think there's really anything like it, maybe even in the world. They have this like big water treatment facility for the oil field up there. And it has like a moon pool inside of it that's open year round. They keep it heated. And so there's like access to the ocean in that building year round. And NOAA put a tide gauge in there. And it's pretty cool. So they can actually measure the tide up on the north slope even when it's totally locked in ice. But as you can see, they're well, for one, their tides are very small to begin with, the celestial tides. But it is much more driven by atmospheric effects. So tide predictions, you know, I'm not gonna say they're useless up there, but it's really only one piece of the puzzle when you're trying to understand the water levels up in areas like that. This is also kind of the case in a lot of Western Alaska, where there's a lot of vulnerable communities out there. And
blue is the predicted tide?
yeah, sorry, the blue is predicted tide, red is the actual observed
Pressure.
tide. Yep.
There was some kind of a big storm in the middle of it.
Yeah, some sort of atmospheric disturbance. It can actually be fairly difficult to totally understand and predict the interaction of the atmosphere with the water levels. It's something that NOAA is actively researching right now. They really want to be able to predict these storm surges in Alaska. And there's a lot of effort going into that right now. So hopefully in the next couple of years, maybe we'll start seeing forecasts for storm surges in Alaska.
Does the ice sheet itself affect the tide at all?
It does somewhat, but less than you think. The ice really is moving up and down with the tides every day. Yeah. Okay, want to talk about sea level change a little bit. And whenever we're talking about sea level change, there is a really important distinction to be made between absolute sea level change and relative sea level change. And I see a lot of especially news articles and stuff that don't do a good job of making this distinction. And it really has well, I'll get to that later. But absolute sea level change is the sea level rising as measured to the center of the Earth. So that has been consistently rising. This chart on the left is showing it measured by satellite altimetry. The different colors is a different satellite taking over the job as one gets phased out and the next one comes online. So that has been going up by about 3.5 millimeters a year and accelerating somewhat. And then relative sea level change also brings into the picture this idea that the land itself is also moving, tectonic movement. And this is especially important in Alaska because we have a lot of tectonic movement here, especially in South Central and Southeast Alaska, where it was fairly recently, in geologic terms, glaciated. So there's lots of ice sitting on the plate, and that ice is melted, and now the plate is kind of bouncing back up. And in most of South Central and Southeast Alaska, the plate, the land itself, is rising up faster than the water is rising up. And so the relative sea level change in those areas is actually going down from the perspective of somebody that lives in that area. You would see the water going down over decades. So to bring it home a little bit, down here at the bottom is the relative sea level change in Cordova since the tide gauge has been operating out here by the ferry dock in 1964 or something, looks like. Again, we have the absolute sea level rise up in the top left. This is data from a GPS reference station that's on Mount Eac. It's kind of by the parking lot there at the ski hill. And it's been running there since late 2005. And this is just the vertical component. So this is showing the land rising about 4 millimeters a year, roughly. So compare that to absolute sea level rise, 3.5 millimeters a year. The land is going up slightly faster than the water. And that's what we see with the tide gauge. So because we have a tide gauge here, we don't actually have to do this math, because the tide gauge is measuring it directly. But of course, you notice this dramatic change here, which is pretty interesting. Before that, the sea level was rising in Cordova. And this is 1987. There was a couple of big earthquakes that happened off the coast of Yakutat that, for whatever reason, I'm not a geologist, but that changed the way Cordova is moving, the plate around Cordova is moving, that earthquake. Pretty interesting.
So, okay, so Drew,
Yeah.
in that last graph, so the land was going, okay, so I gotta get this in my head, right? So
Yeah,
the
so
land's
the time scale here is, this starts at 2006, so that's just like this. Before this point, we can probably assume that the land around Cordova was dropping down.
And so we're not really seeing the 64 earthquake making any kind of real.
I think they put this in right after the 64
Oh, that-
earthquake,
oh,
so
okay, I was
it's,
thinking that,
yeah.
okay, gotcha.
Which is a bummer. That would have been some really interesting observations there.
Is there a tight, how old is the tight station out at Shagwell? Is there one?
Shag Rock.
There is a question of, I thought originally the measurements were taken out there, and then they moved them in.
Huh. So there's been tide gauging projects. I'm going to get to a slide in a little bit that shows all the tide gauging projects done in Alaska, and there are tons of them everywhere. There was one at Orca in like 1899 or something, like before Orca Cannery even existed. I would not be surprised if there was one at Shag Rock at all.
Henry existed in 1895.
Okay, it was probably about the same time then that they did the tide study there. Yeah. Yeah. So actually, jumping into some history of tide gauging, they had to get pretty creative back then. The center photo is from Cook Inlet, actually. Really crazy. I just can't believe they did that, but yeah. Yeah, so before the invention of like automated sensors and recording systems, all the tide gauging was just like a giant ruler in the water and some guy out there writing down numbers for days on end, months.
Wasn't that long ago.
Yeah.
The Valdez.
Right, yeah. Yeah, I've talked
Helped
to
with it.
a number of people at like old canneries and stuff that the predecessor to NOAA would come in and set up the station, but then they would just hire some local person to write down numbers for them. And yeah. Of course, things have changed a little bit since then. So here's a map showing all the tide stations, tide studies that NOAA has records of over Alaska. Gobs of them. But most of them are really old and have very limited data. Like a lot of them are just like a couple of high waters and a couple of low waters written down. Most of the data collected at these green dots is not really useful for our modern applications. So what do we use now? There's kind of two main sensors that are sort of bread and butter for tide gauging these days. We've got the radar sensor and the bubbler gauge. The radar is this thing that you bolt down to some sort of infrastructure on the coast. It points straight down and bounces a radar beam off the water and just measures how long it takes that beam to return. Works kind of like a boat radar. They're awesome, very easy to install, very accurate, very low power, but they have the requirement of needing some sort of coastal infrastructure to mount them to that's stable. And in most of Alaska, we just don't really have stuff like that, except in like south central, southeast. So in Alaska, we rely on these bubbler gauges a lot, and these work differently. They involve this thin hose that's it's an air line that goes into the water and then is affixed to some sort of outlet under the water. And that's what this is here. So this black thing is the air hose going in, and then this is the outlet that we bolted onto a piece of rebar. So this gets driven into the seafloor, all weighed out with a dry suit and pounded in under the water on a low tide. And then the hose runs up onshore into the gauging compartment electronics. In there is a little air compressor, and the air compressor is pumping air through this hose and pushing little bubbles out the end of the hose. And next to the compressor is a pressure gauge, and it's just measuring the pressure that it takes to push those bubbles out. And so really this gauge is measuring pressure. And as the water gets deeper over the outlet, it takes more pressure to push those bubbles out. So we have to do a little bit of calculation to convert that pressure to a depth. But these are nice because they don't need that sort of a dock or like a seawall or something to mount to. We can just go slap it in the mud or wherever. But they are not quite as stable. They have complications if there's like water density changes going on, freshwater inflow or something, or like in an estuary where the water density is changing a lot, because that's part of that equation of getting from pressure to depth. And so sometimes we deploy conductivity sensors and temperature sensors to correct for that if we think it's going to be a big problem. And then the other big thing that we're concerned about is stability of the sensor. Our specification typically with NOAA is that the sensor cannot move more than 6 millimeters, which is not very much. And so, like mounting the radar to something that's wooden that might swell or something when it rains is maybe not a good idea. You really want these rebars to be stuck in there really good.
What about ice?
Yeah, that's definitely a concern. Of course, with the radar, if it's in an ice-prone area, that's not going to work if the ice comes in because it's bouncing off the ice and then not the water. That's another reason that they don't get used in Alaska a lot, except in southeast and south central. The bubbler is not affected by ice unless it literally gets like hit by the ice and moves that 6 millimeters. But it will keep reading as long as the air hose, doesn't freeze up. There can be condensation that freezes up in there sometimes.
How do you know that it moves?
I will go into more detail on that in a couple slides, but we measure them with very precise surveying instruments at the installation and again at the removal. And then we're kind of making some assumptions that it didn't like move in between those 2 points. Yeah. Okay, and then some alternative sensors. We've got, these are kind of less accepted by NOAA. They can be very particular about what sensors you use on their projects. But some newer technologies that are coming out, we've got pressure gauge moorings that is similar to the bubbler. It measures pressure. We throw it on an anchor, dump it in the water, and then it just collects data internally and sits there. But they are very unstable. 6 millimeters is, you're never going to get within 6 millimeters. They're going to be moving around on the seafloor with currents and stuff. So that's always a challenge with those. GPS buoys. This is a cool thing that I've been working on a lot at JOA, designing and building these buoys. This is actually a buoy I built in Cordova here, actually just right out there. And that's got a very precise GPS receiver inside of it, batteries and solar panel, and it just bobs there in the water, and as the water goes up and down, it goes up and down with it and logs GPS data. And then GPS reflectometry is this much newer technology and technique that has been kind of a passion project of mine a little bit. I've been developing this processing algorithm that takes it kind of uses the way that GPS signals bounce off of the water to measure the tide. And it's pretty unique in that it is the only system we really have that can measure the water obliquely, which has a lot of applications in Alaska because nothing has to touch the water. And so it's not going to be affected by ice or strong currents or anything like that. The other cool thing is that it's also a GPS. And so if it moves that 6 millimeters, we know exactly how much it's moved and when. And so now it can kind of move all over the place and still be okay. So that's a pretty cool thing that is an active area of development that JOA has been working on, and a lot of other researchers at universities. I was at the American Geophysical, or I don't actually know what that stands for, AGU. It's like the scientific organization of like geologists and earth scientists in general, and gave a presentation at their conference in San Francisco about it earlier this winter. Okay, so come along with me to install a tide gauge. First, we got to get there. Of course, it's Alaska, and the logistics get crazy up here, and so we got to get creative. Helicopters, boats, float planes, pack rafts, kayaking, hiking, like whatever we got to do to get there. This was a pretty fun trip. We had a tide gauge to install in Hyder, Alaska, which is like way down here, this furthest southeast you can get. And we actually just loaded up the work truck and drove the Alcan highway down there. If you ever drive in the Cassiar Highway, it's a little detour off the Cassiar. Totally worth it. It's a really amazing place. Okay, the next thing we got to do is set up our tidal benchmarks. And so these are these survey markers that we put on land. Usually our specifications are we need at least 5 of them. And these are really what we're measuring the water level relative to. And the intention is for these to be a permanent reference mark in that place. And so any future surveyor can come back and say, okay, in this previous study, they determined mean sea level was X distance from this physical object on Earth, and do whatever work they need to do, or redo the study because maybe they think sea level has changed there noticeably, and you can set up another tide gauge and relate that measurements to the measurements we took. It just provides that stable long-term 0 point for everything that all the water levels that are measured at that spot. This is looping, but it's also very short. So this one did go very deep. I think the deepest I've set these is like 180 feet in Pilot Point. It's actually a jackhammer, so.
Oh, that turn?
It's a Cobra. Yeah. Yep. Yeah, they're pretty sweet. Yeah, so what I'm doing here is we've got these 4-foot long stainless steel rods that I'm screwing on top of each other, and then my coworker is jackhammering into the ground.
How many feet? 4 feet?
Well, usually they go about like 50 down. Yeah, you can be there a while hammering the rod into the ground, especially if you have to do 5 of them. This is what it looks like on the surface here. We cut the rod off just below the ground level there, put a little lid on it. These pink fins that you see here is the sleeve that goes over the top. It's filled with grease. And so as the ground freezes around it and moves, the idea is it's not going to grab onto this steel rod and pull it up. It's just going to grab that sleeve and slide it around. Of course, in Alaska, we have permafrost, and so that doesn't work very well, or really at all, to be honest. I've come back to these and found them sticking like this far out of the ground before.
So you put 5 rows in the ground to be the reference, like the average position of those?
Yep. Yep.
It was one of your ones here in the Fish and Game parking lot.
Fish and game.
There's, it looks like there's a survey benchmark sitting in the parking lot.
I don't know if that would be a tide mark. There is one, well, there's a bunch of them down around the tide gauge area at the ferry terminal. But there's one of these rods that is kind of by a power pole on the left as you're driving into town, right across from, I think it was the old cookhouse, Copper River Cookhouse, right across the street there. Yeah, this was in a place just outside of Golovin on the Seward Peninsula, east of Nome. It's like 1:30 in the morning there.
I used to work fast.
Yeah, I don't know if you can see it. Yeah, in the high res image, you can, everything is kind of like shimmering a little bit. And it's from all the mosquitoes. It was just, and,
It looks like it's swamped.
yeah, it was insanity. Sometimes we go back to these places where surveyors have already been and find their benchmarks. And this is one I found in Golovin a couple of years ago. It's the oldest one I've ever found from 1900, and it was chiseled into the rock here. This is always a really fun part of the job. It's kind of like a little bit of a treasure hunt, yeah, Easter egg hunt. A lot of times NOAA gives us these old like typed or handwritten descriptions that are usually really vague, and maybe a hand-drawn map if we're lucky, and get to go out there and try and decipher what the heck they were talking about in 1900. A lot of times they're referencing like buildings that are long gone, and you gotta go talk to some elder in the village and ask them where this thing was. It can be pretty fun.
So how accurate, like they have a lat long there, if you were to redo that, how accurate is theirs?
That lat long is pretty wildly inaccurate. Yeah, I'm not even sure how they came up with those numbers. Yeah, that as well, yeah. It'll get you to the community. Yeah. And then we gotta install the sensors. So on the left there, that's me driving in one of those rebar things. Over here is a docking eggy where I rappelled down and bolted them to the pilings there. Yeah, got to get pretty creative out there. Yeah.
So is that within your 6 millimeter perimeter time to like
2 pilings.
pilings? It seems like those.
Yeah. Yep. Those ones closed out. But we also had we also installed a radar gauge here and one of those GNSS reflectometry systems right here. So we had 3 different types of gauges going to try and hedge our bets. Actually, down here is a 4th type of gauge. We had 4 gauges going there to really be overly redundant, and hopefully one of them comes out good.
Where was that?
This is Igigik in Bristol Bay. And then we got to survey the sensors and the benchmarks all together, and that gives us that nice stable reference for everything. We use very specialized surveying equipment. It's a digital differential level. And so the rod man is holding basically a tape measure kind of, except our leveling instrument has a camera inside of it and reads this little barcode instead of actual written numbers. I don't actually have to look through it to read the numbers off. I just hit a button and the camera inside reads it. And then we also have really go overboard with it. We've got temp sensors on things that is correcting for refraction of the air changing as the temperature changes. This rod is made out of this really special metal that doesn't stretch or expand as temperature changes. It's pretty crazy technology, and at the end of the day, we're able to achieve consistent measurements down to usually a couple tenths of a millimeter, sometimes even hundredths of a millimeter if everything is perfect. Pretty crazy.
What kind of metal?
I just know it by INVAR, which stands for invariable to temperature. I don't know what the actual like makeup of the metal is. I know it's expensive, and we send it to a particle accelerator laboratory to get calibrated every couple of years. Yeah. And then we've got to verify that the tide gauge is working correctly once we've got it all set up. So this is Trey Losey with me. I dragged him up to Shishmaref on a balmy November day. And we just use our rod in the water and take some manual measurements, just like the old days, writing them down in the notebook and compare that against the tide gauge, make sure everything's good and dandy.
How often are you doing that?
So typically our gauges are measuring every 6 minutes. Kind of an arbitrary number. That's just what NOAA picked. And so we take our manual measurements at the exact same moment that the tide gauge is taking its measurement. So every 6 minutes.
Drew, are these mostly short-term tide gauges as opposed to permanent tide stations?
Yeah. So
It'd be the type of thing like in the back of our tide books, they show the corrections.
right.
And that's where those corrections are places where these temporary tide gauges at some point.
Exactly. Yep. Yeah, so most of those photos I've shown so far are from temporary tide gauge installs. And then this slide here shows the permanent stations that are in Alaska. We also have a contract with NOAA to do some maintenance on, not all of them, but some of them, including periodically the one in Cordova. They try to get to all of them every year. Doesn't always happen. They re-level everything to make sure they got that 6 millimeters. And then, of course, just make sure everything's working well and do maintenance and that sort of stuff. But these long-term stations are really important for kind of what Dave was getting at. That is what allows us to make tide predictions in other locations with a minimal amount of data. If we have a tide gauge that's been operating for a really long time nearby, then we can kind of correlate those patterns to the long-term station and make really accurate predictions with just a month or a couple months of data at a nearby location. I just want to point out there are some massive gaps in Alaska here. If you were to look at like a map of Texas at the same scale, there'd be like tide gauge, tide gauge, tide gauge, tide gauge, tide gauge, tide gauge. It's like kind of crazy, but yeah. And also notice a lot of our most vulnerable communities are in those areas with some pretty big gaps. Okay, I've got 2 minutes. Wait, is that right? No, 15 minutes. Okay, we're good. Okay, so a little virtual tour of the Cordova tide gauge. Let's go check it out. It looks weirdly shrunk, but anyway. You might recognize this kind of rickety-looking building out on the old ferry dock, the fuel dock down there. City-owned building, but they've been generous enough to let NOAA keep their tide gauge in that building. First thing you see when you walk up is, we call it the Met mast, or it's got meteorological sensors on it. Most of the permanent NOAA tide gauges also have some meteorological sensors on them. They've got wind sensors and air temp sensors and barometer. I think that might be it. So this was, I think, 2 years ago. I was doing some of the maintenance on it, and that mast folds down so that we can get access to the sensors on the top of it and check them, replace them if we need to. Those wind sensors are notorious for going bad. And then if you keep walking around the building, there's this door to this little closet basically that has the tide gauge. As you walk up to the door, you'll notice this big white tube here, and that's one of the sensors. It's actually a sensor I didn't really talk about, but it's very similar to the radar. This is an acoustic sensor. They've been phasing these out in favor of the radars, but they work kind of the same way. They sit on top, shoot a sound wave down instead of a radar beam down, and bounces off the water. And then this is just with the lid removed here. If you go up to that and put your ear next to it, you can actually hear it ticking away in there. And then walking into the building, these are the electronics enclosures here. There's like data loggers, batteries, there's solar panel, charge controllers, there's cell modems, there's the AC power source, there's the compressor for the bubbler gauge. Probably missing some things, but a bunch of electronics. Everything is very redundant. And then we also have, or NOAA has remote access into it, so they can log in from their Seattle office and mess with things if they need to. And for the most part, if something fails, there's something else there that will pick up the slack. So it's they're usually pretty resilient. And then if you go and look under the dock, it's kind of weird to get a view there. So these are like shot through my binoculars with a cell phone, but this white tube here is the bottom end of that tube with the acoustic sensor in it, going down into the water. And then this black tube is very rickety looking bubbler tubing going down that is in serious need of some maintenance. And then this next slide is underwater. You might notice this looks suspiciously tropical. This is not Cordova. This is from Hawaii. A couple months ago, we had a crew out there. But it's the same sort of acoustic sensor column going down. And then at the bottom here, there's this sort of fixture down there, and that's where water gets into the tube. And it's got these two plates that are parallel to each other, and that's a design feature to minimize the turbulence of currents going through. And there's kind of a weird physics thing that happens there, like Bernoulli's principle of flow going past the orifice of the pipe. Actually will change the pressure inside of the pipe and suck the water down or push it up higher than it should be naturally. So that's to try and minimize that effect. So the divers go down and they like do an inspection. This video here is like the inspection before they do anything, and then they'll clean off the all the growth, especially around the outlet of the pipe. And then they'll do another video of everything after it's been cleaned, and check all the bolts and everything. Yeah, that's pretty much that. Okay, and that's pretty much it, I think. These last photos here are from Emmerich Basin, which is just north of Nome on the Seward Peninsula. I set up this gauge here, and I knew there was a lot of bears around, so I set up this bear fence, and then I also put this game camera up on there, thinking we'd get some awesome photos of bears walking around. Forgot to turn that on before we left. It's very unfortunate because it got absolutely demolished. Apparently, it did not care about the electric fence at all. But we got the data we needed, so it's all good. Emmerich Basin, it's yeah, it looks almost like a giant lake, but it's actually slightly tidal. It's connected out past Heller to the ocean, and big body of water. It's where it's been in the news lately because they're proposing to do this big graphite mine right there, just north of Nome.
Isn't that the place where they found that one moose that had rabies?
Oh, I think you're right. I think you're right. Yeah.
Rabies, yes.
Yeah.
Wow.
Yeah, there's a lot of rabies in the fox population there now.
Drew, is the dock here where the sensor is, that really doesn't move more than 6 millimeters? I mean, you see something dock against that. And
It's looking pretty rough.
The big stuff comes in.
Yeah.
Yeah,
Some of those big
yeah.
guys getting fuel, it's just like freezing.
Yeah,
The ferries were
right. I don't know. I haven't actually looked at the surveying data from that station, so maybe it does move more than 6, and they're just like, oh, we got to live
It
with
doesn't
that.
really invalidate it, right? I mean,
Yeah,
you're
yeah.
right, it bounces back.
Yeah, especially if the movements are kind of transient, like a boat hits it and it moves and then goes back to its sort of equilibrium point. That's probably okay.
And then, so currently, you can make all kinds of predictions, right?
Yeah.
So the point of carrying on with this is to measure change over time, or?
Right. Yeah, that's a big part of it, is measuring that that sea level change, relative sea level change.
Because like you can predict really far in the future, right, with the data that's currently available?
Yeah, right. The other thing is when we're doing these temporary stations, we need that reference station to be running simultaneously with the temporary station. And so in that case, it makes sense to just have it going all the time.
Yeah.
And then there's also those meteorological effects that are important to have a record of, just understanding the patterns involved there and a record of different events for all sorts of science. Yeah. Sorry.
Leading down a question, what is the elevation where we sit?
Right here. How deep do you want to go? Because that gets to be a very complicated question, depending on like in what reference frame are we talking about, in what and reference frames change over time, so you also got to say at what point in time. Not an easy to give a very precise answer. It gets complicated.
How about just a guess?
Oh, like where this floor is?
Yeah.
I have no idea.
What you see in the book, they reference like mean, low, mean, high, what does that mean?
Yeah, so I didn't really go over that. Those are referred to as tidal datums. And so what's going on there is they're taking all of the water level observations or predictions and just looking at the high points and the low points and taking averages of them in a very certain way. And each of those has a little bit different definition. You've got mean high water, you've got mean higher high water in areas where you have semi-diurnal tides or 2 tides a day. Is that what your
Zero is
question is about?
reference to
Okay.
what?
What's that?
Zero is reference to what? Is that mean, lower, low?
It's whatever you say it is, depending on your application.
In the tide book. what?
In the tide book, okay. Yeah, 0 is mean lower low water in the tide book. Yep.
What's that again? It's mean, lower, low?
Yeah, so if you were to measure the tide in Cordova for, it's actually 19 years. I won't go into why, but 19 years.
6 million.
Yeah. And you took the average of, so there's 2 low waters each day. One's lower than the other. You just took the lowest one of each day, took the average of that for 19 years. That elevation, they say, is 0 in the tide book.
Yeah, you mentioned predicting storm surge.
Yeah.
Are they going to take into consideration barometric pressure?
Yeah, that is definitely a big part of that equation for predicting those sorts of things. Of course, it's not just barometric pressure at any one point. They've got to look at wide areas when they're trying to make these predictions and broad patterns, and it's a pretty complicated system to try to figure out mathematically to the point where you can make useful predictions. And it's one of those things where you don't want to jump too quickly into making inaccurate predictions, or you might start crying wolf a little bit and lose some of the public trust in your predictions. So they want to make sure they have it really good before really making that sort of thing public.
It does have a big effect.
Yeah, oh, absolutely. Yep.
If you've never been to the Cordova website for the tide station, they put on there the predicted tide, like you were showing before, and then on top of it's the actual tide happening in real time. And then you scroll down a little farther and you can look at the barometric pressure in real time. I wish they had them right next to each other. But, anything, starts dropping below 1,000 millibars, and you start seeing higher than predicted tides, where it goes the other way, and real high pressure system, and you get lower than low tides. And it's just fascinating to watch when they set in when the guy who was running the tide stations in Valdez. He had his own little barometer there, and he on his own little piece of paper on the side was doing one of those direct measurement, and then he was doing the barometric pressure. And you have to really understand that. Of course, the old cabin I lived in, the bottom corner of the cabin starts soaking at 15.8, so I'm very connected into where the tide's making with the barometric. And I saw a 3.5 foot higher tide than predicted.
Wow. Yeah, if you go on the NOAA website, this is sort of the chart that you'll see there. And so you've got blue is the predicted water level. This red is the actual observed measured water level by the tide gauge. And the purple here is the difference between them. So you could call that your storm surge.
So do you guys just do the installing, or how much follow-up do you have to do with the data?
It kind of depends on the project. On some projects, we're just doing the installation and removal, and then we just send off the water level data to NOAA, and they do their own analysis. On other projects, we're doing a little more analysis. We're actually calculating those datums, the mean, lower, low water. And rarely we actually do the predictions too. That would be more for like a private client that has some special need. Like one case that comes to mind is we've had clients that are doing aerial mapping projects, and part of their contract is they have to fly the shoreline at low tide in some remote part of Alaska to get imagery or LiDAR elevation data or something. But there are no tide predictions for that area. So they come to us and say, oh, can you give us a prediction of when our flight windows are, and we'll calculate that up for them.
So that horizontal line, that's an observation, not a prediction.
You talking about the purple line here?
Yeah.
The purple line is the difference between the observation
Right,
and the
but is it
prediction.
an observation from the past, or is it that a prediction of the future, like a tide prediction?
The blue line here is the prediction. So on this axis, we have time here. On this axis, we have the water level. The blue line is what's predicted at that point in time. The red line is what's actually measured by the tide gauge at that point in time.
Okay,
The purple is the difference between them.
so they're not predicting the difference until it occurs. and they observe.
Right, yeah,
Okay.
exactly, yeah.
So is elevation of like Mount Eyak here, it's based off of the lower low mean, like at the 0, or, sorry, go back to like this complicated.
Yeah. So that gets into this sort of, usually when they're talking about elevations of things on land, we're talking about like elevations above mean sea level. If you go look at like the elevation of Mount McKinley, they're going to give you this number it's elevation above sea level. We're like, what the heck does that mean? Because there's no ocean there. What's actually going on is it has to do with gravity, and we have these models called a geoid that is sort of like if you were to shovel a trench all the way to under Mount McKinley from the ocean, where would the water be? Is sort of one way you can think about it. The force of gravity is not equal all over the globe. It varies slightly, and that causes water to bulge in certain areas more than other areas. And so what they're actually doing is flying a gravity sensor in a plane or in a satellite all over the planet and figuring out where these bulges are and using that to sort of say, okay, if there wasn't a mountain here, then mean sea level would be at this point, and that's what that elevation is based
So
on.
it's uniform for the whole world, the base that it starts from.
Yeah.
Or they try to.
Yeah, it's not a perfect sphere. It's kind of a bumpy, blobby sphere around the world because of these different gravity anomalies, different rock densities, and magma in the earth has different densities and is flowing around. But yeah. Yeah.
What happened with like in any eclipse event, like the last recent one, the solar eclipse, is the combined alignment of the sun and moon, creating ginormous tides in those events? It would seem like it might.
That sounds right.
It'd be perfect alignment with the
Yeah,
Earth.
right at that point.
It would
Yeah.
seem like their gravitational pulls would get combined.
That logic makes sense to me. Don't write that down.
Your dad could be the one to stump you.
Yeah.
As I recall, though, I think the tides came in less than predicted, though. Right?
Yeah, that barometric pressure
Okay, yeah.
overrides so much. And if
That
it's
makes sense,
predictable,
yeah.
So it was predicted.
Yeah.
The only way you can really predict it is you watch windy.com and see where some of those low pressure systems are coming. And if they're really low and coming right offshore from us, then you get a storm tide.
Right.
So Drew, are there plans to have more tide gauges around? I mean, does NOAA have plans to have more tide gauges? Because it just seems like the places that need tide gauges don't.
Yeah. On one hand, I complain about it. On the other hand, like, I also understand it because tide gauging in Alaska, in those areas in particular, is really hard. There's just like, it's all just like sediment that's getting blown around by rivers, and there's sea ice, and it's just really hard to build something stable that will last long term. USGS has stream gauges out in those areas, so kind of up in the rivers, and they're just continually getting demolished and reset and rebuilt, and so it would be a pretty expensive thing to do. But there's absolutely a need for that that sort of data.
Satellites will probably take over pretty soon. Satellites will probably take over.
Yeah, I mean, yeah, that really is probably the long-term future of tide gauging is satellite altimetry. It's not really there yet, but it's getting better every day.
So the Tide app that I use, if I'm running out towards the flats or whatever, it'll give me like Shag Rock where I'm near there, Gravel Point. I mean, and where does it get all those from?
It's pulling that. Well, so all those tide apps and actually the tide books themselves are not published by NOAA. They're like private companies that are just pulling data from NOAA, I think, probably. Can't say for sure exactly what they're doing, but they're probably just pulling all this data from NOAA's public database. And yeah.
So they can crunch the numbers and spit out something.
Yeah,
that's
yeah.
relatively.
Yeah, if you go on NOAA's website, you can go straight to the source and look at the predictions for that site that NOAA has actually
Any
generated.
of those sites they list, like Shag or Gravel, they probably would have had a short-term gauge at it at some point in time.
Yeah,
right?
yeah,
Maybe
exactly.
for 2 months, 15 years ago.
Yep.
Sort of thing, right?
Yeah.
And that's what we're using, based on the Cordova
Yep.
station.
Do we have any temporary ones right now?
Next week, I will be installing one in Sheep Bay. It's going on I think it's the biggest island in Sheep Bay. I don't think it has a name. There's like a sandy beach on it. That's like the only sandy beach anywhere around. It's like a really nice sandy beach if you see it. It's like, yeah, sunbathing worthy.
What would it take to establish a tide station at Dana's house?
Because I got a high water mark from the 28 or so years that we've been living there on one of my pilings.
Oh,
I didn't
cool.
record the date, unfortunately, but it's a good foot above my yard.
Wow, yeah.
Yeah, but you got the combined, it was
Right,
out, but at
yeah.
a real high tide, it's pretty open, but maybe it holds up some water there, but yeah. Wish I had recorded the date. It was one of those things where.
I'm a scientist, sorry.
I just went out there and put a mark on the pilot.
Yeah.
Who's wanting you to do the one in Sheep Bay?
It's for the state of Alaska and NOAA, kind of a partner project.
Is it for, are they?
No, it's part of a statewide effort. We're doing like a dozen tide gauges all over the state as part of that project right now. It's like a 5-year project.
Anything's happening.
No, I honestly have no idea why they picked Sheep Bay. Yeah, some of those selections are a little odd.
We have a question online.
Okay.
Yeah, hey Drew, it's Mead Treadwell in Anchorage.
Hello.
I'm on the Science Center board, and I haven't had a chance to listen to many of our Tuesday night deals, but thanks for a good presentation. The reason I turned in is my daughter Natalie works with T. Carta. She does a lot of work with your firm, and she's always
Natalie.
Yeah, she's always complaining that we don't have a datum in Alaska. And when I was lieutenant governor, I got all the money started on this as chair of the Arctic Research Commission to do the whole new digital elevation model of the terrestrial map in Alaska. But
yeah.
things like the height of Eyak and the height of Denali, I actually reported that Denali was shorter than the 20,320 that we thought it was, and the
that was you. Okay, yeah.
Yeah,
I've read that before.
that was me, and I got everybody uppity about that, and
Yep.
as it turns out, they refused to change the numbers until we have a datum. So anyway,
Right.
I guess the question is, I heard all the ground level work you're doing, and you were asked once about how many of these we need. What's it going to take all this work that you've done to get us a datum?
Sorry, can you repeat that last part?
Yeah, how long before we have a datum for Alaska based on your work, or the work of these tide gauges that's going on, so that we know what sea level is?
Right, right. Okay, so I think you're talking about VDatum, and that's the project that we've been working on this last year and for the next couple of years. And we just got word from NOAA that they are hoping to have a prototype out in the public by, what did they say? This winter, I think. Sometime this winter, they'll be releasing a prototype for Alaska.
Cool.
Yeah, it's coming. This partnership that we're working with the state on, I think they made a really good move of kind of moving a lot of the responsibilities to the state, because I get the feeling that things are actually happening now.
Yeah. Good deal. Well,
Yeah.
thanks very much for educating me a lot. I really appreciate it.
Yeah, you bet. Thanks for tuning in.
Okay. Bye-bye.
Oh man, I had a lieutenant governor watching me.
Got some reach there.
Good job, Drew.
Hey, Shan.
Good job.
Thanks. Yeah.
Hey, I got a request for some samples out at.
Oh, yeah, for sure.
I've actually got the tour upstairs, and I haven't looked into it, to get the exact location, but by any chance, it's near where you are, would you be willing, they're looking for a bunch of mussels.
Oh, yeah, for sure, yeah.
Okay.
Definitely, let me know.
Yeah, any chance you can stop by tomorrow and we can see Ray came there?
Yeah.
I may end up having to leave quickly,
Okay.
and that's why tomorrow's the best day to get hold of me.
Yeah, okay. Yeah, I'll swing by tomorrow.
And I'm here early.
Okay.
I tend to leave about 3, 2:30.
Okay, yeah.
Yeah.
Sounds good.
Anytime early in the day.
Sounds good.
But it's really good seeing you.
Yeah, yeah. Thanks.
Good to see you too. I remember
Yeah. Oh, yeah.
If you can find out what the elevation is here, that'll be a good reference point.
Okay, yeah. I'll calculate.
Dana's house, anyway, we all, I forget to do it, make a list sometime.
Yeah, yeah.
Very good, very good presentation.
All right, thank you.